This is a sound wave. And here's another one. Let's put them together. We now get this new sound, and it feels a lot more harmonic. When you put many of these frequencies together, you get the more complex sound you hear in music and films and games every day. That's pretty cool, but what if for audio analysis, I just wanted the bass? Or just the main instruments? At first glance, it seems I can't easily do that, because all these frequencies and amplitudes are jumbled up together, and you can't just unmix audio that's already been mixed. Well, it turns out it's still completely possible, with this incredibly useful formula we call the Fourier Transform. You may have heard of the Fourier Transform, but if you haven't, it is crucial to breaking down waves by their frequencies. It works fundamentally because of constructive and destructive interference. Say we have a mixed signal, containing both 10Hz and 20Hz sound, and we want to extract only the 10Hz signal. Our transform will analyze and multiply each amplitude by the amplitude the target frequency is. So it will look at the amplitude of perhaps the 10Hz component and see that it's positive when the target 10Hz frequency is also positive. So 1 multiplied by 1 gives us 1. Continue forward and we see that they become negative at the same time. So -1 times -1 is also 1. Since both are the same, they experience constructive interference, and essentially they reinforce each other, causing the 10Hz signal to isolate from the rest of the sound. But let's take a look at the 20Hz signal, which is travelling up and down twice as fast as the target 10Hz. It's positive when the 10Hz signal is also positive, but becomes negative much faster than the 10Hz signal. 1 times -1 is negative, so they experience destructive interference and cancel each other out. This concept is exactly what makes the Fourier transform work. To understand how we get the Fourier transform mathematically, let's take a look at the complex plane for a second. The horizontal axis is the real number system, and the vertical axis represents complex numbers, which we can refer to as j in code. We can plot a point, like 1 plus 1j. Using polar coordinates, we can represent this point with its length from the origin and the angle it makes. Euler's equation states that when you have an angle theta, e to the power of j theta is the cosine of theta, representing horizontal step, plus j times sine theta to represent vertical step. If we keep increasing theta, you might notice something interesting going on with this point. It's travelling anti-clockwise around the centre. Once theta hits 6.28, which is 2 pi in radians, the point has made it all the way around. This is actually tracing a unit circle, and it's making full revolutions at the rate we increase theta. So let's set theta to 2 pi to represent a full revolution, and multiply it by k, a specific frequency like 10 Hz. We can change this frequency and make it maybe 18 Hz or even go as low as 2 Hz. The point is that making it go higher or go lower changes the rate at which this point moves around. Now we want this point to specifically make a full revolution once all the audio data has been analysed. Let's say capital N is the total number of samples we need to perform, and lowercase n is the one we are currently on. We divide 2 pi by capital N, and multiply our frequency by lowercase n. And finally, we want this point to travel clockwise, so we make j negative. This seems like a weirdly complicated expression, but what we've made is a point travelling around a unit circle at any frequency we want. This is our target frequency, just like the purple wave from earlier. So all we have to do is multiply this target by the sample we're currently analysing. If x is our array of sample data, x of n is the amplitude to compare. Let's multiply them. Now we can sum up all the constructive and destructive interference going on using sigma notation. And there you go. This right here is a discrete Fourier transform. It takes in a sample of amplitudes, compares them with our target frequency, which by the way we call a Twiddle factor, and then leaves the rest of the unwanted frequencies to go through destructive interference. So let's actually see how this transform works in action. Here's a basic cosine wave with a frequency of 2, but in a computer you won't see continuous data like this, so instead it's represented through our X array. Here it just has 8 samples, but in reality there'll obviously be many more. Let's substitute all our values in. This gives us a Twiddle factor that's also oscillating at the frequency of 2. If we combine our waves and carry out the transform, we get this summation for each sample. All the imaginary j's have cancelled out, and we're left with a positive reinforcement for this frequency. Now if we try only a frequency of 1, our summation becomes this. We're still left with none of the imaginary constants, but all the waves have destructively interfered, so they cancel each other out. So now we have this clean visual representation of our sound, but right now it's just a bunch of numbers we multiply and sum together. As for how we'll turn each back into its own distinct sound wave, we'll have to get to that next. We first need to figure out how to actually get a computer to do this maths in real time without crashing or being too slow. The DFT forces a computer to check every single sample against every single frequency. That's an O of n squared operation. If you try to run a whole song through this, your computer has to do trillions of calculations. The audio would stutter, freeze, and completely break. And so would your computer, probably. To fix this, we use the Cooley-Tukey Fourier Transform, or the FFT for short. It was designed by J.W. Cooley and John Tukey, and uses a lot of traditional computer science tricks to make the Fourier Transform so much faster. Instead of processing the entire song at once, the FFT cuts the audio into packets we call frames. We're going to use a frame size of 1024 samples, each sample being a measure of the amplitude of the sound, by the way. Because our audio is recorded at 44,100 Hz, so about 40k samples per second, each block is a fraction of a second, roughly 23 milliseconds. Here, the Cooley-Tukey algorithm will do something conceptually similar to merge sort. It splits our 1024 sample block into smaller pairs of even and odd indices recursively. To do this incredibly fast and right inside the computer's memory, we use a function called bit reverse. It takes each binary index and flips its value. So for example, index 1, which is 001 in binary, becomes 100, or index 4. This new order for binary samples cuts that O of n squared into O of n log n with base of 2, by using the same calculation results for where the amplitudes happen to be the same, which given that it's a wave is pretty likely to happen a lot. For a 30-second clip, we cut the computer's workload already by nearly 70,000 times. Once all the data is shuffled, the code runs it through a butterfly network. It gets its name because if you trace the path of the data on paper, the lines cross over each other to form a shape that looks exactly like a butterfly's wings. Instead of computing all 1024 samples at once, the algorithm solves the problem across 10 sequential stages, since 2 to the 10 is 1024. In each stage, the code merges smaller solved subproblems into larger ones. Stage 1 first pairs up individual samples next to each other, and then it applies a DFT to only that small 2-sample pair. Stage 2 merges those pairs into blocks of 4, and then into 8s, and then 16s, and so on until we reach the 1024 sample frame again. But how exactly does this merging work? To combine the two streams of data, we grab an element from the upper half of our block, let's call it U, our even index data, and then we grab an element from the lower half, which we multiply by our spinning Twiddle factor to get the rotated value, T, which is our odd index data. Because circles are symmetrical, spinning a Twiddle factor halfway around the circle is the same as multiplying it by I squared, or minus 1. This is what allows us to use the exact same calculation result again to get both the upper half and lower half of our block. We can calculate T once, and reuse it again for two completely different outputs. We add them together to get the upper path, and subtract them to get the lower path. Just like that, we have compressed our DFT to work much faster, across many samples using just addition and subtraction. Once the FFT finishes processing, it outputs an array of 1024 complex numbers called frequency bins. You might naturally assume that a 1024 sample frame would give you 1024 distinct frequencies to play with, but a phenomenon called conjugate symmetry means that's not really true. Because our raw input audio has only real numbers, just simple physical amplitude measurements over time with no imaginary components, the output of the FFT becomes a perfect mirror reflection. The first half of the array, bins 0 to 512, represents our actual audible spectrum, scaling from 0 Hz up to 22,050. The second half of our array, bins 513 to 1023, contains the exact same information, but backwards. You can think of them as negative frequencies wrapped around the circle on the complex plane, but we have to maintain this symmetry for the audio to remain audible. If you turn up the bass, you cannot just scale the low frequency bin in the first half of the array. If you forget to modify to mirror in the second half, you break the symmetry. And when you give an asymmetrical spectrum into the inverse FFT to rebuild the sound, the imaginary parts of the complex numbers won't cancel out like they're supposed to. That'll leave imaginary parts behind in our audio data. So as our loop iterates through all 1024 bins, we keep another variable called k_effective to track the frame index we're currently processing. It mirrors the index backwards once it crosses the 512 midpoint, so if k is 924, k effective becomes 100. We guarantee that the second half of the data mirrors the first half, so imaginaries cancel out in the end. Now that we've successfully isolated our frequencies, applied our equalizer gains by multiplying a specific frequency by a gain factor, and preserved our mirror symmetry, it looks like we're finally done. We have a modified spectrum, but it's still sitting in the frequency domain, meaning if we were to plot the data we get back from it, our x-axis will be the frequency, and our y-axis will be the magnitude. So to actually play the audio out of our speakers, we need to convert these frequency bins back into the time domain. So time progresses along the x-axis, and we see how our amplitudes change along it. To do this, we use the inverse fast Fourier transform, or the IFFT. It uses this equation. It looks almost identical to the forward FFT we just broke down. It still uses a butterfly network, and it still processes data in 10 sequential stages. And it still pairs up elements using u plus t and u minus t. But there are two small changes that cause this function to do the inverse of the forward FFT. Firstly, our twiddle factor now has a positive exponent. In the forward FFT, the negative I, or the negative j, meant that our twiddle factor was spinning clockwise around the complex unit circle, since that's the convention for polar coordinate systems. So flipping that sign flips the direction this point moves around the circle. And because our butterfly network loops through 10 stages of adding and subtracting values over and over again, the amplitudes of our points get inflated again. They scale up by a factor exactly equal to the total length of our frame, which is 1024. So this means each amplitude point is 1024 times as loud as it should be. The solution is to just divide each value back to what it should be. So it looks like we've solved how to split a sound wave by its separate frequencies and then reconstruct it again. But if we just ran our modified blocks back to back, we would hear a clicking noise happening 43 times a second. The FFT assumes each frame starts and ends with an amplitude of 0. But in reality, each frame almost always starts and ends differently. So this leaves rough edges, and at every frame we hear a click. To fix this, we introduce the Hann window. Before the audio even hits the FFT, we multiply the block by a smooth bell curve, which is given by this equation. This gently fades the boundaries of each block down to silence, and that smooths out the discontinuity. But if we fade the edges to 0, aren't we losing audio data? To solve that, we implement overlap add. Instead of jumping forward by 1024 samples, our loop only steps forward by 512 samples, which is a 50% hop size. When the inverse FFT converts these modified frequencies back into real sound waves, these overlapping fades are added back together. The overlapping curves sum up to exactly 1 across the entire timeline, and this keeps our audio perfectly seamless, continuous, and still without clicks. Cool. We've gone through how we can use a lot of code and a lot of maths to deconstruct almost any wave we want. As for how we go further with this, I'm building an entire project called Audiergon, and it allows you to do many interesting things with audio files using the Fourier Transform. You can plot the transform in the frequency domain and see visually which frequencies are more dominant than others. For example, here we can tell the song is quite bassy because the lower frequencies have a much higher amplitude. You can also compress audio files quite a lot by realizing that high frequencies are nearly impossible to hear when you have other frequencies that are much louder. And if there's some low-pitched hum in the middle, in pretty much every modern audio analysis tool you can just play around in the EQ filter, and you can turn that frequency right back down. So yeah, that's a look into how the Fourier Transform works in computer science and audio analysis. This was a more theory-based video, so I do plan on making a part 2. I'll be going through the code I wrote and I'm still writing for Audiergon, plus how I've deployed it to the AWS cloud for practical usage online. Anyway, thank you so much for watching and I hope to see you soon.